All right, so today I'd like to talk about it's part of the subject called combinatorics, which means the science of counting. And so we're going to count certain things today, and the answers we get might be a little bit surprising, a little bit bigger than we'd expect, but this is going to be very useful when we study the binomial distribution at some point. So, combinatorics. Okay, so it's a rather large subject. It's the study of counting. So there's a lot of things we can count. So what we're going to mainly be interested in today is permutations. Okay, so permutations, that's a word that comes from the word permute. So if you have several objects in a certain order, you can permute them in a way that will change their order. And so we basically want to know how many ways we can order a certain number of objects. So the example I'd like to do is for a daycare. So let's say we're managing a daycare with 15 children. Okay, we want to manage a daycare with 15 children, and we want to line them up before they go to lunch. And the question is, how many ways can we line up 15 children? Because you know they're going to be upset if somebody's first or somebody's second. So how many possible ways are there that we can line them up? And that's basically how many ways they can complain about the way the line is. Okay, so if we're trying to line up 15 children, well, we might pick who goes first. And then, well, how many options would there be for who goes first? Well, if there's 15 here, I can take that one of the children and put it first, right? So there would be 15 options there. Okay? Now, who would go second? If I have one away, then there's 14 left, right? So there's 14 left, so there's actually 14 options for who goes second, okay? And for who goes third, well, you already have one picked out for first, another picked out for second, so there's 13 options for that, and so on, okay? So our answer is, we could calculate our answer by multiplying all these together. These technically, who we choose to go first and second, are not independent choices, but the fact there was 14 choices was independent of who was picked first. So we can just take the product of all these numbers to get our answer. So the answer, if I wrote it out without working it out, and see, you can see how this is rather long to write out. I'll probably go off the screen, right? It's 15 times all that. Now, I worked out what this is ahead of time, and it's if we take the product of all these numbers, we'll get 1,307,674,368,000. That's it. Okay, there's over 1 trillion ways to line up those 15 kids. Okay, so now mathematicians are not going to want to write down this number ever, more or less, right? I put it up here to give us an idea what all this multiplied together is. All this multiplied together is. All right? And mathematicians don't want to write down all these numbers multiplied together. That's almost more writing than what's below. So there's a notation for when we want to take 15 times 14 times 13, and that notation is to write 15 with an exclamation point after it. Now, if you're reading this for the first time, you might say this says 15, right? Because the exclamation point puts an inflection on it. But a mathematician would read this as 15 factorial. So 15 factorial is equal to that. So some smaller examples might be 4 factorial, which is 4 times 3 times 2 times 1. Now, I don't need to multiply by the 1. It won't change the value, but this is 6 times 4, 24. So that's much more manageable. But in this case, when we're lining up 15 kids, it's 15 factorial, which is this huge number. Good. Now that's if we're just lining up everybody in our set, okay? Lining up everybody in our set. Let's do another example of where we want to talk about how things could be permuted. A different way of phrasing this answer is that there's over 1 trillion ways of permuting 15 objects. That's one way we could phrase what we've learned on this board. Okay, so let's do another example where we're not trying to do everybody at once. So this example has to do with the Anglers Alliance. Okay, so that's a group. That's just basically a group of people who like to fish, right? You might have a hobby and want to join in with other people with that hobby, and that's the Anglers Alliance. And so in this hypothetical Anglers Alliance of Manchester, say, just a small little group, there's 7 members total. Okay, so there's 7 members total, and they want to, this Anglers Alliance, as far as their little club goes, they want to elect a president, a vice president, okay, and also a treasurer. Okay, now how many ways can this Anglers Alliance elect a president, vice president, and treasurer? Well, it's similar to lining up the kids. We have 3 slots here. We have a president, a vice president, and a treasurer. And let's say the person can only hold one office, which is, for any sane organization, that's what they should do. If 2 people are in one office, maybe it should, or in 2, if one person's in 2 offices, maybe they should combine those offices. So, well, if we pick a president out of 7 members total, whereas if all of them are willing to run, there would be 7 options, right? And then once we've chosen a president, then there's 6 options left for whoever's next, and then 5 options left for whoever's next. So we get a much smaller answer in this case. We get 7 times 6 times 5, okay? And that's, we can work that out to be 210. Now, mathematicians like formulas, and you might notice 7 times 6 times 5 is not a nice standard formula, but we can use this notation with factorials to write down this number, okay? You might see 210 that's arrived at by figuring out a number like this, written as 7 factorial over 4 factorial, okay? Now, you might see it written as 7 factorial over 4 factorial. Now, it turns out it's going to be equal to what's above. And let's go ahead and work that out. It's 7, top it's 7 factorial. 7 times 6 times 5. Okay, and I'll just switch to red. Times 4 times 3 times 2 times 1. Okay, and then if we divide this by 4 factorial, it's 4 times 3 times 2 times 1. So everything that's in red will cancel. Let's use this one. Everything that's in red will cancel, right? And we're left with just a 7 times 6 times 5. Okay, so you might not immediately want to write down 210 this way, but it's nice because what if you were talking in general about the Anglers Alliance with next year they had 200 members because they did a really good job getting people to go to their fishing events. And maybe they have 5 offices next year. You can still figure it out, like with 100 members and 5 offices, it would be, let's say, n members in our offices, this number would be n factorial over n minus r factorial. Okay. And so that's the permutations of different books refer to this different ways. This number might be referred to the permutations as it might be referred to as the permutations on 7 objects taken 3 at a time, or the textbook we use in our statistics course will say the number of permutations of R objects selected from N objects. Okay, so this will be very helpful, and especially this notation, we'll need that when we're looking at the binomial distribution on our next